So in this video, we're about to prove one of the most fundamental theorem of functional analysis. That's the Anbanak extension theorem. Here it is. What is the theorem telling us? It tells us that if I have a linear continuous map that is defined only on a subspace of my Banach space, but satisfy the definition of continuity with constant 1 here, say, then such a linear map can be extended to an element of the dual. So something that will be equal to L of x on the subspace, but is defined on the full space. And the constant in this inequality, that constant 1, will not increase in the sense that the norm of L star in capital X star would remain less or equal to 1. Now that looks almost obvious, right? You have something that's defined on a subspace. You can just extend it maybe by 0 on the directions that you're missing from this subspace. But it's not that obvious in infinite dimension. In finite dimension, sure, you could just look at the other directions and extend by 0. The same would be true if you had a closed subspace of a Hilbert space, for instance, because in that case, you have an orthogonal complement. You can extend by 0 on the orthogonal complement. But in Banach spaces, you don't have this notion of having an orthogonal complement. In fact, we'll see that sometimes it's not even possible to project on a closed subspace. So you cannot separate what you're doing on the subspace from what you would do on the rest of X. So we'll have to have a way to construct a matching version of L without increasing the norm, adding directions to the subspace V. That's going to be the proof of this theorem 4.5. And it's a very helpful theorem because from there's all sorts of geometric intuitions that you have from finite dimension that you can extend to any Banach space, really. So we'll have two corollaries that show us the sort of thing that you can extend thanks to the Anbanak theorem. For instance, you can have a norming functional. Now, what does that mean? If I have a vector in Rn or even in a Hilbert space, I can always find its norm by testing the vector against an element of the dual. I just have to look in the direction that X is pointing at. So I can take the element X star of the dual, if I'm in a Banach space, to just be X itself divided by its norm, and I would have that X star X gives me the norm of X. But you can't do that in a Banach space in general because you don't have a inner product. But you can always find, nonetheless, an element of the dual that's going to do exactly the same thing. It's going to have norm 1, so it's an element of the unit sphere of the dual, like direction in finite dimension. And when you test X against X star, you get back the norm of X. That's what we call a norming functional. The existence of such thing is a consequence of the Anbanak extension theorem. In the same way, you have the fact that adjoints of bounded linear operators are well defined. Bounded linear maps themselves between the respective duals with no increase in norms. So if I have a bounded linear map between two Banach space, I can define a bounded linear map between the duals, so going the opposite way from Y star to X star, and the corollaries can tell me that there's a well-defined way to do that, and that gives me a bounded linear map from Y star to X star with the same norm as T. And the way you do it is through what would be a property of adjoints in Hilbert spaces with the inner product, but that becomes a definition here. So you define the action of T star on an element Y star of capital Y star. It as an element of capital X star, so it's a linear function on X, so you have to tell me what it does to an element of X. And what does T star Y star does to X? Well, it gives you the following real number. Apply the functional Y star, which is an element of capital Y star, to T of X, which is an element of Y. So that extends the idea of taking adjoints of matrices or of bounded linear operators in Hilbert spaces to general Banach spaces. And this is compatible with the topologies. That's what the topology given by the norm. That's what these corollaries tell you. So this would be some more intuitively correct result that we want to extend. They are not obvious, but they would be consequences of the key theorem from today. So before we prove it though, I'd like to attract your attention to this little proposition that I've put first because it's a much more elementary way of extending a linear map. And that's when you extend from a dense subset. So when you extend from a dense subset, a map that restricted to this subset is linear and continuous, then, well, things are pretty easy. You can just extend by continuity. So you can define, say, the limit of t of a limit of a sequence to be the limit of t of that sequence. That's the idea. So this theorem is telling you that when you have something defined on a dense subset, you can always find a unique continuous linear extension. And I'm going to leave the proof of that to you as an exercise. It's a very good exercise. It's elementary. It only uses Cauchy sequence and linearity techniques, no deep ideas. But first of all, this proposition is extremely helpful in practice. Usually you only look at maps on subsets that are dense but are made of sufficiently nice object for definitions to make sense, and you focus your attention on proving an estimate. This is very often the case in analysis. And once you have the appropriate estimate, then such a basic proposition kicks in and gives you the definition of the object, more generally speaking. So I'll leave that as an exercise. How do you prove it? Just a hint. Well, you give yourself a vector in X, take a sequence xn in S that approximate that X. T of xn is going to be a Cauchy sequence because of this property. Cauchy sequence converge. The limit of T of xn is going to be what you want to be, T of x. But you have to do various reality checks. You have to show that it doesn't depend on the choice of approximating sequence, that the limit is linear, that the limit is continuous, and that it is unique. So I'll let you go through that exercise, and we're going to focus our attention now in proving the much harder extension theorem when the subspace is not assumed to be dense. Let's have a look at this. So let us prove the extension form of the Anbanak theorem. Now, there are two steps to that proof. And in the first step, what we do is we add just one dimension to our subspace V, and we construct an L star that matches L on V, and that is well defined in that extra one-dimensional subspace. Now, once you know how to add one dimension, what you want to do in step 2 is run some kind of an induction process to keep adding dimensions until hopefully you've covered the entire space. Now, if the space is separable, that's pretty easy to do. That's literally just an induction argument. If the space were to be non-separable, then this gets a little trickier, and we have to use Zorn's lemma and a little bit of set theory to do that. But that's only in the case of Banach spaces that are non-separable, which are not particularly common beast, at least in my experience. Okay, so let's start with this first step where we see how to add one dimension to our space V. Now, let me first of all point out that without loss of generality, we can assume that V is not X, because if V is X, then I take L equal L star and I'm done. So assume V is not all of X, and then in step 1, I can pick a vector V1 that is in X but not in V. And I can consider the subspace V1, which is spanned by both V and the vector V1, right? So you add the line spanned by V1 to your vector V. Now, in that subspace, what I need to know is what L star of V1 should be. If I define L star of V1, I extend by linearity, I'm going to have a definition of L star on V1, capital V1, if I can define little L star on little V1. So let's find out how we can choose a value for L star of V1. So for that, I'd like to remark the following fact to start with. If I take U and V in my vector space capital V, and I look at L of U plus L of V, well, that is L of U plus V, and because of the bilinearity and because of the assumption, a sort of continuity assumption on L, this is smaller than the norm of V plus U, and therefore by triangle inequality I could add and subtract V1 and say that this is less than u minus v1 plus v1 minus or plus v1 plus v. Okay, now reorganizing that a little bit, you find that L of u minus norm of u minus v1 has to be smaller than L of v minus L of v plus norm of v1 plus v. And well, you could take a supremum of a u, you could take an infimum of a v, and you would still get a large inequality, an inequality in a less or equal inequality, and because this holds for every u and v. So what we have is that the supremum of all u in v of L of u minus norm of u minus v1 has to be less or equal than the infimum of all little v in capital V of minus L of v plus v1 plus v norm of that. So, okay, the supremum of a u is less or equal than the infimum of a v. They may be equal, or they might, or the inequality might be strict, and in which case there is an entire interval of value between the two. So what I'm going to do now is I'm going to pick a real number, let's call it r, in that interval. That interval might be reduced to just a point, in which case I only have one choice for r, and if it's not reduced to one point, then I have infinitely many choice, and you just make one. Right, so I pick an r like this, and then I'm going to define L star of v1 to be this value of r. So potentially there are many possible values for L star of v1, and therefore L star is going to be very much non-unique. But that's not the problem. I didn't say anything about uniqueness. I just say there is an extension. Okay, so I define L star of little v1 in that way, and then I have an obvious definition for L star on capital V1, and that is the following. Any element of capital V1, of course, is an element in V plus some multiple of V1, and so I'm going to send that to alpha times R plus L of V. Right, so I'm defining it this way for V in V and alpha in R. Okay, that's my definition of L star. That's clearly linear by construction. And it's also clear that L star of little v is L of v for all v in capital V, because a v in capital V can only be written as v plus alpha v1 by taking alpha equal to 0, because v1 and alpha v1 is not in V. So what we need to show now is that L star of v plus alpha v1 in absolute value is always going to be smaller than the norm of v plus alpha v1, and that should be true for all v in capital V and for all alpha in R. Now the point of that is to show that this new L star, which is an extension of L, not to all of x quite yet, but to v1, satisfy the same continuity assumption as L, and that's going to allow us to iterate that argument and keep adding dimensions in case v1 is not equal to x quite yet. So let's prove that. So let's take a v in V and an alpha in R. Actually, let's not worry about the alpha quite yet. Let's just take a v in V and take alpha equal to 1 to start with. So what can I say about L star of V plus V1? Well, it is equal to, by definition, R plus L of V. Now that can be positive or negative. So what if it is positive? So if R plus LV, is positive, then what can I say about the absolute value of L star of V plus V1? This is LV plus R. Now you got to remember that R was what? It has to be smaller than this infimum here. So it's smaller than this for any choice of v, in particular for this choice, this particular v. So that is to say that my LV plus R has to be smaller than L of V plus minus L of V plus norm of V minus V1. Sorry, plus V1. And then the L of V cancel, and that is exactly what I want, V plus V1. So, right, that since R is smaller than the infimum of the all, let's call them W in V of the quantity minus L of W plus V1. Okay, so we have what we want in the case where R plus LV is positive. What if R plus LV is non-positive? Then my L star of V plus V1 in absolute value is going to be minus R minus L of V. Now R is greater than the supremum, so minus R has to be smaller than minus, and I can choose a V, and I'm gonna choose minus L of minus V. What is it? Minus V minus V1. Right, that's using the fact that R is greater than the supremum of L of U minus V1 in norm. Okay, and that's minus L of V. Now by linearity of L, minus L of minus V is L of V, so the L of V cancel, and what have I got here? I think I did mess up my sign. Oh yeah, sorry. Yeah, no, I did not mess up my sign. I've got minus here and minus there. So this is literally equal to norm of V plus V1. Right, so in both of those cases, positive or non-positive, we've proven what we needed to prove here, at least to alpha equal to 1. And now, well, how do I get it for another value of alpha? Well, that's easy by linearity now, because L star, so for all V in V and for all alpha in R, when I look at L star of alpha V1 plus V in absolute value, this is equal to alpha R plus L of V, and this is equal to absolute value of alpha times R plus L of V divided by alpha, unless alpha is 0, but if alpha is 0, the inequality is trivial. And then I can apply the previous step to R plus L V over alpha and get that this is smaller than alpha mod alpha times norm of V over alpha plus V1, which, minus plus V1, which is equal to, I really have problems with sign, which is equal to V plus alpha V1. And that concludes the proof of the claim. So what we have is that L star of alpha V1 plus V in absolute value is smaller than V plus alpha V1. So if V1 was already equal to X, then we are done. All right, we found our L star in X star. Now, if it's not, then we're going to iterate the process, get V2 in V3, and so on. Now, by induction, if X is separable, the theorem is proven. Okay, now we're going to move to step 2, and we're going to show a more fancy version of induction using a set theoretic argument that would allow us to get the result even if X is not separable. So step 2, let's see how this fancy induction argument works out. So we know how to add one dimension to V, or even countably many dimensions to V, just iterating the argument we've seen in step 1. Now, how to conclude from that? Well, this is a typical use of a set theoretic tool called Zorn's lemma, which tells you that if you have a partially ordered set and every totally ordered subset has an upper bound, then such a totally ordered subset with an upper bound will have to have a maximal element. So let's run that for the problem we're trying to solve, which is the problem of extending our linear functional L. So what have we got? I'm going to define the following. So if I have a pair that is a subspace of X and a linear map from that subspace into X. So W is a subspace that's actually that's included in V, that includes V. So I've expanded my V in some way by adding dimensions with step 1, and W is a subspace, and I have a map from that subspace into R, which is linear and well satisfies the assumption of the theorem, of the same assumption as L. So it's an extension of L. So it's L on V, and it has the same constant in the continuity inequality. So for every y in W, the absolute value of LW of y is controlled by the norm of y. So I'm going to define for such a pair. So the pair is, I'm extending from V to a larger subspace, and I'm extending the linear function L to a new linear functional L star, like we've done in step 1. And so given such an extension, I'm going to define a partial order relation that says that this extension WLW is smaller than another extension W prime LW prime, provided that two things happen. Well, first of all, W prime is a larger subspace than W. So it still has to be a subspace for it to be a pair in the sense that I defined before. And LW prime is really an extension of LW, as in it matches LW on W, right? So this order relation tells me that I'm really extending. I'm making the subspace bigger, and I'm getting a linear map from the bigger subspace that matches the linear map I had on the smaller subspace. Okay, now let's take F to be a totally ordered set of such pairs. Right, now obviously not every set of such pairs is going to be totally ordered. You can have subspaces with no inclusion relation between them. But let's assume I have a totally ordered set. Now I want to show that such a set has an upper bound to satisfy the assumption of Zorn lemma. So I'm going to define W tilde. How do I get my upper bound? Well, I have sets, they all have an inclusion relation, so I can take the union of all those sets over all pairs in my family F, right? And that's going to give me a subspace because of the total ordering property. Now, okay, so given any element in W tilde, any vector in W tilde, because it's defined on that union, there has to exist a W that depends on X and an LWX, an element of F, such that X belongs to W. Right, and so I'm going to define LW tilde to be what? To be the map that sends X to LWX of X, right? And X is in one of the W's, and then I just use the linear map that I have on that W, LWX. Okay, so this is well defined. And now what have we got? We've got that this is an upper bound for the set F. Right, is an upper bound for F, because if I take any element in F, well, any subspace W will be included in this gigantic union of all of them, and then any linear map would be extended by this, because it would be equal to LW on W. Okay, and of course, because it is just an LW for the appropriate W, it satisfies this defining property of having constant 1 in discontinuity inequalities of my linear functional. So what have I proven? I've proven that with respect to this partial order of pairs of subspaces, and linear maps from the subspace into the real, any totally ordered subset of such pairs as an upper bound. So Zorn's lemma exactly tell me, by Zorn's lemma from set theory, I have that there exists a, let's call it W bar, with its linear functional, and a pair such that, so a pair in F, given any F that is totally ordered, that is maximal. And what does that mean? That means that if I give myself any W prime and LW prime in F, they're going to have to be smaller than W bar, LW bar. So we're going to have that W prime would have to be included in W bar, and LW bar of Y would have to be LW prime of Y for all Y in W prime, right? That's what having a maximal element for that particular relation means. Okay, so this maximal element is going to do the job for us, basically, because, well, there's two possibilities. This massive set here that I have in my maximal element subspace, it may be all of X or it may not be. So if it is all of X, then we are done. Then we can take L star equal LW prime, and that does the job. And the proof is concluded. Now, if it's not the whole set, well, then we can extend it by step 1. Then we pick a W1 that is in X but not in W bar, and construct W bar 1 LW bar 1 by step 1. And then what do we get? Well, we get that there exists an extension of W bar LW bar. And so that gives that W bar LW bar is not maximal. And that's a contradiction. Okay, so this concludes the proof. Now that's a pretty fancy set theoretic argument. I personally have no problem with the axiom of choice, but people who do not like the axiom of choice typically don't like this type of arguments. That makes doing functional analysis a little bit harder for them. That being said, this is not critical to our mission here. We'll be almost entirely working with separable Banach spaces. Maybe L infinity, the space of bounded measurable function, will be the one counterexample of a non-separable space that we might have to deal with, but we won't deal with it as a Banach space particularly much. So you could just run a simple induction argument rather than Zorn's lemma if you wanted to. Nevertheless, this is the general proof, and we now have our extension version of Handball theorem. So now that we have the extension version of Anbanak theorem, we can prove some neat little corollaries, and the first one is the existence of a norming functional for any vector in X. So how do we do this? Well, we're going to define what it should be just on the span of X, and then we're going to extend it by Anbanak theorem. So, okay, I pick an X, and I define L that goes from the span of that single vector into R, and take something of the form alpha X, where alpha is a real to alpha times the norm of X. All right. Now L is linear, and L of alpha X in absolute value is what? Is absolute value of alpha times norm of X. So, and that's exactly the same as norm of alpha X. So this satisfies the assumption of Anbanak theorem. So using Anbanak, I can find a element X star in capital X star, which has norm 1 and which extends X. So X star Y is equal to L of Y for all Y in the span of X. So in particular, you have that X star X is L of X. And what was L of X? Well, it was exactly designed to be norm of X. So that, oh, actually, sorry, the Anbanak theorem only gives me that X star as norm less or equal to 1. It does extend, it gives me a norming functional. I'm not 100% sure that at this stage that the norming functional has norm 1, but of course it does, because X star of X divided by norm of X is exactly equal to 1. So the norm of X star has to be greater or equal to 1. And that's it. That's how you get your norming functional. You define it in the obvious way on just a one-dimensional space spanned by X, and then you extend it by Anbanak. Okay, that's a very typical application of the extension theorem. And as a corollary of that corollary, actually, we get the fact that the adjoint operator defined in the somewhat obvious way, using the duality product the way you would use the inner product in a Hilbert space, is a well-defined bounded linear operator from Y star to X star with the same norm as T. So let's see how that works. So for one direction, I'm going to just pick a Y star and capital Y star, and an X in capital X, and then I'm going to look at T star, Y star, comma X. I need to show that this is smaller than a constant times norm of Y star times norm of X. That will prove that T star is a bounded linear map, and the norm of that operator T star will be smaller than that constant that I'm going to get. So, well, this is by definition Y star applied to T of X. Now, the definition of the norm in a dual space is that it's the supremum when you test against vectors of norm 1. So this is equal to Y star T of X divided by norm of T of X multiplied by norm of T of X. Okay, that's if the norm of T of X is non-zero. If the norm of T of X were to be 0, well, this entire thing would be 0, which is smaller than anything I want. So without loss of generality, I can assume that T of X is non-zero. And now this is certainly smaller than norm of Y star times norm of T of X, right? Because I'm testing Y star on a vector that has norm 1. So this is smaller than the supremum of a Y star of applied to Y for any Y on the unit sphere. And now by definition of the norm in the space of bounded linear maps from X to Y, which is also defined as a sup, this is smaller than the norm of T and B of XY times the norm of X. And that is exactly saying, because this is true for every Y star and every X, that the norm of t star is smaller than the norm of t. That's the norm as a bounded linear map from y star to x star. That's the norm as a bounded linear map from x to y. Okay, that's good. We need to prove the reverse direction, which is a little harder, but that's where Hahn-Banach will come to the rescue. So for that, let's give ourselves an epsilon, and let's pick an x that almost realizes the norm of t of x, the norm of t, sorry. So I'm going to pick an x of that has norm 1, and such that the norm of tx is almost the norm of t. And by almost, I mean up to this epsilon. That's why I gave myself an epsilon. The norm of t is the supremum of the norm of the tx over all x's on the unit sphere. Now that supremum may not be a maximum, but I'm just taking an x that's close enough to that, to realizing that supremum. And once I have that, okay, then corollary 1, which is really just a corollary of Anbanak, tells me that I can find a y star and capital Y star that has norm 1, and that is such that y star t of x is exactly the norm of t of x, right? I'm taking a norming vector y star for that vector t of x, which is a vector in y. That's exactly what corollary 1 provides me with. But now, okay, now what have I got? I've got that norm of t of x is greater than norm of t minus epsilon. I'm repeating myself a bit here. And what can I say about the norm of t star? Well, the norm of t star is certainly greater than the norm of t star applied to y star. There's a lot of norms here. So this is the norm in the space of a bounded linear map from y star to x star. This is the norm in x star, right? Of course, because y star, remember, is on the unit sphere, and this is the supremum of all the t star y star for all y star on the unit sphere. And now this here, again, it's an element of x star, so it's also defined as a supremum, so it is greater than t star y star applied to anything on the unit sphere, including that x that I've been looking at in this part of the proof. So this is greater than this, or minus this. So this is greater than the absolute value, because minus x will be also an element on the unit sphere. And now this here is equal to y star applied to t of x. Is that what I want to say? Oh no, sorry. All I need to say at this stage is, using the fact that y star is a norming functional, this is equal to the norm of t of x. But the norm of t of x, as we rewrote right here, is greater than the norm of t minus epsilon. And epsilon was arbitrary. Right, so you could send it to 0, and you get that norm of t star. It's a bounded linear map from y star to x star is greater or equal than the norm of t. And so we have inequalities in both directions, which concludes the proof. So these two little corollaries are perfect example of what the Anbanak extension theorem can do for you. It's pretty clear that this is about constructing a functional of norm 1 with certain properties. Now, in the next part, in the next video, we will see that there's some fancier and more profound, in a sense, geometric consequences of Anbanak. And this will be what we call the geometric form of the Anbanak theorem.